Hello everybody, welcome back to another video of Mr. Coder, and in this one I'm going to show you how to solve beautiful array, question E from Codeforces Round 954 Division 3. So you're given an array of integers a1 through an and an integer k. You need to make it beautiful with the least amount of operations. Before applying operation, you can shuffle the array elements as you like. For one operation, you can do the following. Choose an index I and make a of I equal to a of I plus k. And the array b1 through bn is beautiful if bi equals b of n minus I plus 1 for all I. And find the minimum number of operations needed to make the array beautiful or report that it's impossible. So basically what this means of when is the array beautiful, that basically means that it's almost like a string palindrome. So like the first is the same as the last, the second same as the second last, and so on. So if we look at this first test case with this like huge K, it doesn't matter because there's only one number and that's already the same. So it's 0 since it's already beautiful. For the second one, we can make it beautiful by doing 83,966,524 operations. So this just proves that you can't manually like go through it. Like you can't just like go through each one and add one. You'll have to like quickly do it. Find the number of operations because these numbers can go up to 10 to the 9. And then for this next test case, you can rearrange it. So the 3 is in the middle. You can do it 2, 3, 1, which then if you add 1 to this one here, then it'll be 2, 3, 2, which is a beautiful array. So if we notice something that for a number to be equal to another number, it has to be like if you subtract, like for example for this 2 and 1, you can make them equal with this k because 2 minus 1 is 1 and 1 is 1 mod 1. Well, actually, like 1 over 1 is 1, 2 over 1 is if we use like the mod operation, then 1 mod 1 is 1, 2 mod 1 is 1. So that means we can make these equal. And even though 1's not really a good thing to use, but for example, if we use this 3, then 3 and 9, we can get 3 because we can do plus 3 plus 3. We can do it twice. And we can see it quickly by doing, if we mod it by k, for example, 3 mod 3 is 0, 9 mod 3 is 0. And for example, like 2 mod 3 is 2, and then 14 mod 3 is also 2, which means that you can still get from 2 to 14 with operations. And another thing to note is that if n is odd, then you'll always be having one number that you won't need to find another thing for a palindrome for. So yeah. And for what I did, so first I sorted it because you can greedy through. Like for example, if you had a group of like 3, 9, 27, and 30. So I'll just write it down. So 3, 9, 27, and 30 as like a group of like stuff you can increase together. I mean, you can always like you can make these all to each other. So like you can have this on one side, this on the other side. So then you always want to greedily do it. So you always want to sort it like this. And then you'd get the least 2, 3, 9, 2 operations, and this. This will be 1 operation. And you never want to like, for example, do this and this. Like that's never optimal. So you always want to greedy through it. So that's why I sort it first. And then I create a map that maps the mod value with a vector. And I push back that value after I mod it. And then I get the number of odd. So then I can odd plus plus, because then if the number of odds is greater than or equal to 1, or if it's greater than or equal to 2, I mean, if it's greater than or equal to 1 and n mod 2 is 0, it can't be 1. That was just an overlook by me. But if the number of odd groups is odd length vector groups is greater than or equal to 2, then it's gonna be impossible, because then there will be no way. Otherwise, you keep a variable total, and then you loop through the map and you get the size. And the truth is, this x value doesn't really matter. It's just to help reference this in log n time, because maps have log n operations rather than O of n operations, so that's why it works. And the x doesn't really matter, it's the vector y that matters. And then you have the size, and if the size is even, then you can just go through each pair of 2s, like here. Like you can just go through groups of 2. And since it's already sorted, since we push back and sorted order, since it's already sorted, so it's already sorted. So then you just do y of I plus 1 minus y of I over k. And they're guaranteed to be divisible by k, whether it's 0 or k or 2k, because we already sorted that based on the mod. So then we add that all up into the total. Otherwise, this is where it gets more tricky. If the size is even, or I mean, if the size is odd, and there's only going to be one odd group. So then what I did was, first I calculated how long or how many operations would it be for if you decided to get rid of the first, or put the first one in the middle, and then this is to put the, well, this is to put the first one in the middle, this one's to put the last one in the middle. And then I get the minimum of that. But then, like that, of course, it won't work for the 10th test case. It'll get 15 instead of 14. So that's why instead, you also need to look at the other ones too. And then how can we do that? So for example, if we had indexes 0, 1, 2, 3, 4, 5, and 6. So then we could always have one in the middle. So yeah, we can go through any 0, 1, 2, 3, 4, 5, 6. We can choose any of those to get rid of as the indexes. And we would always have like groups of 2 for like the things you have to match. So, and there are multiple groups. For example, like if we assign like the groups as the starting points, then we can have 0, 2, 4, 0, 2, 5. And then there would be 0, 3, 5. And then there'd be 0, 3, 5. And then there would be 1, 3, 5. And there might have been more that I missed. But like these are like the things that for the starting points of these. And then if you notice something, like it's 0, 2, 4, 0, 2, 5, 0, 3, 5, 1, 3, 5. So like if we decide to pull these out, so we can have this array of 0, 2, 4, 6, and then we can have this array, that'll be 1, 3, 5. And then like we can do suffix sums on this. We can do suffix sums, and then we can do prefix sums on this. So then we can get this. So for example, like 0, 2, 4, we get the prefix sums of this. Well, actually, there wouldn't be this 6 because it has to be all starting points. But you'd get the prefix sums of like 0, 2, 4. And then for this one, you'd get 0, 2, and then you'd get the suffix sum 5. For this one, you'd do the prefix sum 0, and you'd do the suffix sum of 3 and 5, and this 1, 3, 5, you'd have nothing here, and you'd have this whole thing. So yeah, so that's how you use prefix sums and suffix sums. So then if we look at my code, I use the prefix sums and suffix sums with not the best code for that. but well, these 4 lines are important, at least in my code, because that prevents like if the size is 1, then it'll get an error since I'm doing 0 indexing on prefix sums, which I wouldn't recommend using 0 indexing. 1 indexing usually turns out better. But since I started using 0 indexing, I just kept going with it. So I had to do this because I, of course, have this, which if the new size becomes 0, you can't access it. And then I calculate prefix sums. Well, for this is like 0 and 1 starting. So 0 and 1, which then I have the suffix sums and prefix sums off that. Because if we notice that for what I had 0, 1, 2, 3, 4, 5, 6, then for the prefix sums we do 0, 2, 4, and for the suffix sums we do 5, 3, 1. So we have the zeros, which is even, and ones, which are odd, and that's basically what this is for. And I do the prefix sums, and then if the I is even, then it's just simple, like you do the prefix and suffix, because then I'll be splitting it in the middle. But then if it's odd, then I think it'll be better to draw it again. So it's 0, 1, 2, 3, 4, 5, 6. And note that I'm using 0 indexing. So if it's even here, then we can get rid of it, and we have prefix here, suffix here, and it's already groups of 2, so you won't need to worry about it. So that's why it's pretty easy here. But then when it's odd, then if I is not equal to 1, so if we like erase this, if we so if we just say had this 1, if it's not equal to 1, because then there's nothing here, and we worry about the 0 later. And then for the suffix, we do this. And if it's 5, then we can't do that since it'll go out of bounds. So that's why I have these if statements. And then I add this y of I plus 1, this one, subtract it from this one, and divide it by k, since then you need to create a link between these two if you're going to remove this. So yeah, and then you get the minimum of that, and then you add the minimum to the total. And then after you finish all of those groups, and then you just print out the answer. And then that's how you solve a beautiful array. Question E from Codeforces Round 954, Division 3. So yeah, thank you for watching this video. If you like this video, please like and subscribe, and I'll see you in the next one. Bye.